So after 4 seconds, I'm further over here, still traveling to the right. Now, one of the reasons why I picked the same shape is because I wanted to make a big fuss about labeling. If someone gives you a graph and doesn't say what's being plotted, it tells you absolutely nothing, okay? If you have that shape, but you don't know if it's position or velocity or something else is being shown, what do you have? The motion could be this, it could be this, it could be something else. You have no idea. So if your lab instructor, for instance, is a stickler for you putting on the labels on your axes and your units, it's because graphs are meaningless without them, all right? So that's one reason why I picked the same shape. The other is much more practical. I've taken the slopes already. I know the slopes. The slopes will just have different meaning now. So the slope, again, I'll call them segment A, B, and C. The slopes we found were +3, -1, and 0. But now we should examine what exactly does that slope tell us. Well, slope is rise over run. And rise over run here, now it's a change in velocity over change in time, right? So what is that? That's acceleration. So hopefully you believe me now that taking the slope of this graph will lead to acceleration. So these are accelerations. +3, -1, and 0 are the accelerations now. What does the graph look like? It looks just like this, except for its acceleration, right? Now, are these jump cuts okay? Now they're okay, right? We said that acceleration, we allow it to jump from one value to another without necessarily having to go in between. So this is now a realistic situation for the maximum complication for the course. Of course, you could still make the argument that you can't put your foot from the gas to the brake instantaneously, but we're not going to talk about delta A over delta T. We're not going to talk about how acceleration changes. That's where we cut off and limit how crazy we get in this course, all right? So let's go ahead and throw those accelerations in. The acceleration during this part was apparently +3 meters per second squared. The acceleration here was -1 meter per second squared, and the acceleration here was 0. So let's do the head check. My velocity was to the right during this segment. It was to the right during this segment. It was to the right during this segment. What happens when the velocity and acceleration are in the same direction? Speed up. Did you speed up? Yep. During the next segment, the velocity is still to the right, but the slope, so acceleration, is negative. So what happens when the velocity and acceleration are opposed? Slow down, and that's what you did, right? And then we have a velocity but no acceleration in the last segment. What happens if you have a velocity and no acceleration? The velocity stays what it is, right? So here we have constant velocity. Okay? So hopefully you believe me now that the values being plotted on one graph become, if we take the slopes, those become the values plotted here. Okay, so then we took the slopes of the velocity graph, and the slopes became the values being plotted here. All right? Now, the last order of business, I need to show you how to do the reverse process, area under the curve. So let me show you how to get from this back up to this. All right? Let me clear some room for this last bit. So when I say area under the curve, the area under the curve literally means what is trapped between my graph and the horizontal axis. So that would be the area under the curve under segment A. This would be the area under the curve for segment B. And this would be the area under the curve for segment C. Okay? Now for us, because this isn't a more advanced class, those will always be easy areas to compute. They won't be weird shapes. They'll just be triangles, rectangles, or triangles stacked on top of rectangles. That's it. Okay? So let's do those. So for segment A, it looks like this. The width of it is 1 second, and the height of it is plus 3 meters per second. The formula for the area of a triangle is 1/2 base times height, so 1/2 base times height. And if you look at the units, seconds cancel with seconds, we'll get plus 1.5 meters. Now, it came out to be in meters, and that is going to be the only proof I have for you that what this quantity actually represents is displacement. So that is displacement during segment A. And I'll explain to you why it's displacement in just a moment. Now, one of the things, if you don't believe me, that taking the area under the curve leads to displacement, you can verify it with your constant acceleration equations. I'll give you an example, right? You have the initial velocity, final velocity, and time. So that's 3 things, right? That 3 is the minimum of our constant acceleration equations, and we have 3 from the graph. So you can go over here, for instance, plug in v initial, v final, and time, and get the displacement, and you can try it, it gives you the same answer. Okay? So that's the displacement that you've undergone during segment A. Let's do it for B. B looks like this. It's a triangle stacked on top of a rectangle. Both of their widths is the same, because of course that is the area of the curve under the next second. This thing is 1 meter per second tall, and this thing is plus 2 meters per second tall. And so add up the area of the triangle and the rectangle, and let me just tell you what the answer is. It's plus 2.5 meters. That's the displacement you have during segment B. Segment C looks like this. That's the rectangle. That's probably the easiest one. Just a rectangle. It's 2 seconds wide, and it is plus 2 meters per second tall. This one's perhaps the easiest to see because base times height ends up being rate times time. Yeah, I think. So yeah, the height times the base is rate times time. So if you go 2 meters per second for 2 seconds, what's your displacement?
Meters.
4 meters. So that's your displacement during segment C. So anytime you find the area under the curve over some time interval, it'll give you the displacement over that time interval. Let's go ahead and sketch these into our thing here. I found the displacement for each one of these segments. I found the displacement for this segment was plus 1.5 meters. It's to the right. That's good. I'm moving to the right. From here to here, displacement was 2.5 plus 2.5, still moving to the right. And then here, displacement was plus 4. If you wanted the displacement of the entire trip, you'd add them all up, right? That would be like taking the area under the entire curve, and that would give you the displacement of the entire thing, right? So that's how you get displacement information. However, remember what we wanted was not displacement, we wanted ultimately position info. What x value does this whole thing start at? Who knows? No information given about that. So x initial, what is it? Okay, let me give you an analogy. Someone calls you up on the phone, and they give you all this velocity information. They say, hey, I'm going 0 meters per second, now I'm going 3 meters per second, now I'm going 2 meters per second, now I'm going 2 meters per second. And then at the end of the phone call, they say, hey, where am I now? I'm like, I don't know. You didn't tell me where you started, so all that velocity information can't tell me where you ended. So if someone gives you only velocity information, you don't know where they're starting that velocity from. That is, in fact, a problem anytime you move upward. Okay? So if you're taking the velocity graph and you're trying to recreate this, someone is going to have to also tell you what is x initial separately, because it's not included on the v graph. The v graph tells you velocities, but it doesn't tell you where you start having them from. So that's actually, by the way, the same thing when you're trying to move up from acceleration to velocity. So it's like someone calling up on the phone and saying, hey, now I'm going 3 meters per second faster than I was before. Now I'm going 4 meters per second than I was before. And at the end they go, what's my final velocity? And you say, I have no idea what initial velocity you were making those changes from. So you'll always need to be provided with initial conditions when you're trying to work your way up. Okay? So one of the standard things that you would need to be provided with, in addition to this, all this nice fancy information about velocity, is what position did you start at? So let's go ahead and just say it's 0. So this is given separately. Okay? That is not a piece of information on the graph. It's a separate given piece of information that is necessary for you to construct the position graph. So now, notice this entire graph did not have a number line. Now I can overlay a number line, right? I can say that this is x equals 0. Now I know where x equals 0 is. So what's my x location here? What position am I at? Plus 1.5 meters. I start off at 0. Then I displaced 1.5 meters to the right. Now I'm at 1.5 meters. What x value am I at here? Is it 2.5? No. I went 1.5, then I went another 2.5. So I'm at, if I can add, what is that, 5?
Yeah.
Now I'm at x equals plus 5.
It's 4.
4. Okay, I can't add. Thank you. All right. And then where am I at the very end? 8. So notice that this is why position is a continuously indexable thing, right? You can always build upon the position that you start at, but you're indexing where you are. Whereas displacement is something you've done, okay? You've displaced yourself 2.5 meters over this interval, but x is plus 4, okay? So don't forget to make that distinction between displacement and position, okay? So x is something that you build upon, whereas displacement is something you do, okay, between two different endpoints. So let's go ahead now and construct the position versus time graph from that. Looks like this. So I need to leave enough room for 4 seconds. 1, 2, 3, 4. And it looks like I need to leave enough room for 8 meters on the vertical. 1, 2, 3, 4, 5, 6, 7, 8. And looks like I have, should mark off 0, 2, 3, 4 as well. let's go ahead and do it. Put in our points. At t equals 0, I'm at x equals 0. After 1 second, I'm at 1.5, so that'd be about here. After 2 seconds, I'm at 4. And after 4 seconds, I'm at 8. Connect those with a straight line and go home. Oh, they don't all fall on the same straight line. Can I just connect the dots between them then? No, I can't. Okay. So what do we do? Well, remember that the slope of this is velocity. Okay. So the slopes here have to match the velocities. Now my velocity went from 0, 3, 2, 2, so my slopes here have to do the same thing. My slope goes from 0 to 3 to 2 to 2. So I put little approximate markers of what the slope should be at those points because the slope represents the velocity, which I know because I worked backward from velocity. So that gives me a nice roadmap for curving. These are curves. It looks like this. It curves up, then it curves back, and then it's straight. Of course, the slope over the entire last segment is constant because the velocity is constant. So it curves up, it curves down, and then it goes straight. Because when the velocity is changing, the slope has to change here. It causes it to curve. This is the most complicated type of graph that I can have for you. And the reason why is because, just to give you a synopsis, this can be curved at best because this has to be linear, because the slope of this, which is the acceleration, has to be constant. Okay, so that's pretty much it. Now, don't get me wrong, the acceleration has to be constant. It can be constant positive or 0 or negative. It just has to be constant. It has to be flat. And so the velocity here can be a constant slope, a positive, constant negative slope, or even constant 0 slope. But it has to be linear. That's the most complicated it can be. And so when you go over here, the best it can do is curve. It can curve like this or like this. Sorry, this is getting faint. It can curve like this or like this or like this or like this. But that's the most complicated it can get. Okay. With that, in the next 5 minutes or so here, I do want to go back. I mean, this is obviously has a lot going on. It has 3 different accelerations, right? 1, 2, 3. Let me show you what the graphs look like for the projectile motion stuff I was doing earlier. So I want to show you the graphs, and then once I've shown you the graphs, there's no surprises. There's not a whole lot left. Are there any quick questions before I clear a little room for that? Okay. So let me go back to the example I started today with, which was a level ground example. So level ground graphs. So we go back to that example. What do the graphs look like for that? Let's take a look. I'm going to set y equals 0 down here, and the plus y to be upwards. Before, I only had to set plus y being upwards. I didn't need to set a 0. Because as I mentioned, I'm doing all this stuff with displacement. So we don't need to set an origin. The only reason I'm setting an origin now is for graphing purposes. So what does this look like? The acceleration graph, super easy. All the acceleration graph looks like that. Even on the way up, on the way down, the acceleration is all the same. That's all we needed to do. That's the acceleration. All right, let's do velocity. the velocity we said went from plus 10 meters per second to 0 at the top to minus 10. So it might look something like this. Plus 10, 0, minus 10 might look like this. These are the points. Guess I should label this meters per second. Can I connect those with a straight line? Yeah, because what's the slope? Acceleration, which is constant. So graph looks like this. Slope is negative 9.8 meters per second squared. What is that graph actually telling me? That graph, I start off with a positive velocity, then I slow down to 0, and then I speed up to negative 10 meters per second. Notice that that entire thing can't happen under a constant slope. From here to here, my velocity is positive and my acceleration is negative. When I'm heading towards this crossing, right, I'm going slower. When I'm heading to the crossing of the horizontal axis, that's v equals 0. So anytime I head toward that, I'm slowing down. But then, with that same slope, same acceleration, I can cross it and go faster. Because down here, the velocity is negative and the acceleration is still negative. So when I cross that horizontal axis, it represents when I stop. When I go towards it, I'm slowing down. When I cross and go away from it, I'm speeding up. Finally, the position graph, y versus t. I start off at y equals 0. I go up to some maximum value, and then I come back to 0. I don't connect them with a straight line. I remember that the velocity has to be the slope. So the slope will be plus 10, 0, and minus 10. And that gives me a roadmap how to connect them in curves like this. So that right there is your position graph. Now, this is just for level ground. What would you do differently if it wasn't level ground? Just use various segments of this. Let me just quickly show you. What if I dropped it and just let it fall? Well, it'll just be the second half, right? So the second half would just be this part, right? It would just be this part, and then the acceleration, well, that's constant anyway for the whole thing. What if it was a flight where you landed higher than you started, right? What if you finished right here? Well, then you chop that part of the graph off, right? You don't finish it, so you chop off this part, you chop off this part, you chop off the end, right? It's the same graph, just use segments. What if you landed below where you started? Well, then the acceleration stays constant for longer. The velocity goes more negative than positive. So it has a smaller positive part and a larger negative part. Over here, this would keep going as well. You'd have to go to negative y values, or probably more likely, you'd reset y equal to 0 down here, and then it would look like this. You would start like this, right? So you'd finish at the end at 0, but you'd start at some positive y value. It's the same exact question every single time, just taking various segments. Once you know you have projectile motion, the graphs are very straightforward. The acceleration is this, the velocity is something like this, and the position is something like this. So you have some of those questions as well on your homework. Okay, so that's it for today. That's also it for homework number 2.